of them down. So I have items which you will and will not write. We call this 12.1 day 1. And the goal is just to first understand this idea of how do we write a notation of a limit, and then how do we find the limit if it exists from a table or a graph. And we're going to be working with limits for the next 2 weeks. So if today is successful, I think the rest of the next couple of weeks will be good too. All right. So how do we find a limit? First, let's talk about notation. Now, I don't want you to write all of this. The only thing I really want you to write right now will be all highlight. All right? So we got to start off and just say, what happens if I have a function f? Okay? Well, f has real numbers a and l, and we'll talk about where those come from. But I'd like you to write down this part right here. It's an informal definition of what a limit is. And that's the only thing you're going to need to write down on this slide is what I highlighted in yellow. It says L is the limit of f of x as x approaches a if and only if, and this is just our notation. So what we're going to do is we're going to dissect the notation. It's probably going to make no sense to you right now, but we'll get there soon. And what I'd like to also do is we're going to draw a little graph that's going to kind of help us figure out what this is all talking about. All right. So this LIM, that stands for limit, right? Nothing special there. Well, what is f of x? F of x is our function. And when we say function, that means there's an x and y relationship. Now, functions can be graphs, they can be tables, they can be equations. So we can give this to you in many different ways. But let's say that I have a graph here, f of x. Okay, just some random graph as x. Now notice the x value here. That's my inputs, right? This is, think of this as your independent variable or your input. So what happens as I approach the letter A? Now A is a number, right? A is a real number. So what happens if I approach A on the function itself? Where are we headed? Well, we're headed towards an output. Right? So if I go over A and up, we have a location. Now, the big question here is, does a limit exist? And if so, how? Because it's not just reading a point. Right? It's not going over A and up L. What we're going to do, and you don't have to write this, and I think you're going to feel like you want to, we're going to do this so many times today that steps 1, 2, and I think there's a third. No, only these two pieces are going to be very routine. Okay, so as x gets closer to a from both sides, now watch what happens. I'm on the function f. As I approach it from the left, I'm getting closer and closer to an output. Right, I'm getting closer and closer to L. As I approach the function from the right, I'm approaching it, and I just so happen on the example that I drew, I'm getting closer to that same output, L. Now, the values of f of x get closer to L. They may equal L, but they don't have to, because we have open and closed circles that the point exactly at A might be filled in right there, or it might be completely gone, or it might be removed and placed somewhere else. There's a lot of different options for what's happening exactly at A, but what we want to do is we want to talk about as we approach this value A. And the big thing that you need to know is when we talk about the x value here, That's the inputs, right? That's my x values, which are moved left to right. My answer to the limit is the output. That's the y value. Now, how do we evaluate this? Well, if I get closer and closer to a from both sides, that's going to get me closer and closer to this output, L. So let's actually dive into this a little bit more. So we're going to explore this idea with tables first, and then we'll relate back to a graph. I will mention, in calculus, they want you to think about things 4 different ways, mathematically. They want you to be able to think of it graphically, numerically, which is tables, algebraically, which is equations, and then verbally, which means you can write out your full explanation and justification. And that's usually the hardest one, is how do you write about math? But we're just kind of getting to the basis of this. Okay, don't write this. I just want you to kind of look at it. I knew my font here was not going to be great. Let me see if I can make this bigger. I have to get better at getting my tables, my computer at home to my computer here at school matching up. All right, so let's look at this. We have a graph. Okay, we have a function. We actually know the equation of that function. So f of x is the parabola x squared plus 3. They want me to explore the limit as x approaches 2 of the function f. Now it's more than just what is the value go over 2 up 2. Okay, it's more than just the value. So we have 2 different things we want you to really focus on. When you see f of 2 right now, I hope you're thinking algebra 1 right here. All this is the point. It's a location, right? It tells me to figure out when is x equal to 2 and what is the output at that spot. So this would be up 1, 2, 3, 4, 5, 6, 7. Now notice, if I plug 2 in here, 2 squared is 4, 4 plus 3 tells me the location. Okay. I'll erase that. Now, sometimes the limit matches the point exactly. Sometimes it doesn't. In this case, that's what we're going to explore. So, what if I had a table and I want to see this part right here? As x approaches 2, this little arrow stands for the word approaches. All right, now, if I approach 2, I have 2 options. I can approach 2 from the left-hand side. Well, what numbers for x are less than 2? Those are the numbers like 1.9, 1.99, 1.999. All of those numbers are to the left of 2. So what we can do then is, what if I actually just grab a table and plug in 1.99 into the equation? Grab your calculator right now and just try it. Do 1.9 squared plus 3. You get 6.61? Okay. Now, that's kind of close to 2, right? But can't we get closer? Try 1.99. Square it, and then add 3. You get 6.9601. But can we get closer? We can get closer to 2. What if I pick 1.999? You can get closer as well, right? Now, this could keep on going because you could do 1.9999, 9999, You can keep adding 9s, and you get closer and closer and closer. And what you're actually doing is you're getting so close to this dot that you're approaching the output. And if you do that, what numbers do you think we're eventually going to get close to? If I keep increasing, getting closer to 2, what do you think my output is going to hit? We get close to 7. Will it ever hit 7? Not until I get to exactly 2. So if I get close to 2, it's going to approach 7. Now, so I'm thinking that this answer is going to get closer and closer to 7 as I come in from the left. Well, what if I look at numbers not from the left, but from the right? So what if I start taking numbers that are bigger than 2, so like 2.1. Let's try that one really quick. Do 2.1 squared. Yeah, I want you really quick. And then add 3. Did you get 7.1? But notice that's just the higher than 7. Well, 2.1 is kind of far away. What if I do 2.01? You get 7.0401. Now still, that's close to 2, but we can get closer. I can do 2.001. And hopefully you're seeing, you know what? I'm actually approaching the same number from the left side as I am the right. And eventually, if I can find that exact spot, the limit itself is approaching 7. Now, I know what you're thinking. Can't I just plug 2 in? I don't need a graph. I don't need a table. Can't I just plug 2 into the equation and get my answer? That's yes, if the function is continuous. Now, we're not going to get into this whole idea of continuity, but notice, if I want to draw a continuous function, that means I don't pick up my pencil. Right? I was able to draw that graph without picking up my pencil. But what happens if this point right here at 2 is not equal to 7? Everything else is exactly the same, but they said, you know what? Now, your point's down here. Now the limit would not equal the point. And that's where we're going to head today. So, let's take a look at another one really quick. So, same idea. Let's start first with the point. F of negative 2. Here's my function. I'll make this a little bigger. So what I'd like you to do, oops, this should be G. I want you to find G of 2 right now. If I just gave you that, and I said find G of 2, what would you do? Negative 2, I'm sorry. Thank you. Let's take a look. If I'm asked to just evaluate this, what we would do is plug in negative 2. You might notice something right away. Something we really don't like about this problem. Like that bottom. I don't care what the top is. The top's going to turn into a number, but the bottom is 0. I can't divide by 0, so according to the equation, this does not exist. It's not possible. However, the graph might be defined differently. They may redefine it. They might put a point up here. But in this case, we have a number, whatever that's going to be up top, divided by 0. So it's undefined, or we just say does not exist, which sometimes we can call it DNE. You'll see us abbreviate that a lot for does not exist. Well, does the limit exist? Let's think of this from a graphical standpoint. If I look at this limit, here's my function g, and g is the line that's given. This says as x approaches -2. Well, we got to first figure out where's -2 on my graph. As I approach it from the left and I approach it from the right, are those headed in the same direction? Which means the limit is going to exist. But we can confirm that with the table. Now, this is a lot of work to just plug in these points, right? So we're not going to have you guys do that. I'm just going to quick show you. Delta Math has a really friendly feature. I'll show you in a second on how to do the table itself. But if I plug in -2.1, so this is approaching values from the left of -2, the numbers that are more negative. So I'm coming in from the left-hand side here. I get 1.9. Now what if I go even closer to -2? I get 1.99. And if I go even closer, plug in x equals -2.001, I get 1.99, which means I'm getting closer and closer to approaching that value. Well, if we approach the other direction, what if I come in from the right-hand side? I'm going to take numbers that are greater than -2, like -1.9. When I plug that in, I get an output of 2.1. Now notice, if I asked you to graph all these points, you would go over to wherever -1.9 would be. So I'd go like right here, and I'd plot a point. And then I'd go to the next one, and I'd get even closer to that one. I go to the next one, I get even closer. So as I keep plotting these points, they're getting closer and closer to the same value, and the left-hand side and the right-hand side are going to meet. And they meet. Now, the limit itself is going to approach 2. You see that's where the outputs are headed. I'm going to get closer and closer to 2, but will I ever actually reach 2? No, I can't, because 2, the output of 2 is undefined because there's a hole in the graph. So, here's the part I would like you to write this part down here. I'm not going to write every single thing on this slide. But when does a limit exist? Okay, a limit, which here's the notation, a limit exists only if the one-sided limits on each side are equal. Another way to say that, does the left-hand side equal the right-hand side? If the left-hand limit equals the right-handed limit, and they're approaching the same output, then that limit exists. All right, now, when we talk about the one-sided limits,
One-sided limits are when we just look at one side of the graph, so approaching it from the left side or the right side. And there's a new notation. I definitely want you to write these two right here. All right, so we kind of know that if there is just x going to a, that means both sides. This is sometimes called a two-handed limit because there's no direction, so you have to approach it from both sides. But if you have an extra little mark right here, see this little negative sign? It's in the kind of like the exponent spot. That means we're approaching it from the left-hand side. If there's a plus up there, that means we're going to approach it from the right-hand side. So this slide is just getting us used to the notation. I'll give you a second to get that copied down.
So the one thing you have to be very careful with is notation. When you look at this, the two-handed limit is just as x approaches a. There's nothing in the subscript up there, but here we now have a negative. That tells me to approach the function from the left-hand side of whatever a is. And then, if they switch it on us, and they put a little plus up there, we're going to do a right-hand side. And notice, it doesn't tell us the sign value of a. A could be negative, so there could be a negative in front of A, or there could be a positive in front of A. But up top, you have to be very careful just with what values are present there. All right, you don't have to write this. This is just, if we say A approaches from the left, you're coming from the left-hand side of something, same thing from the right. I don't love that, so I wouldn't write it. All right. So let's look at this, because to be honest, the big thing today is getting used to notation. So what if we have a graph? Okay, on a graph, a limit exists as you approach A from both sides. You are also approaching the same height, L. Remember that height, or output, is when you follow the graph with your fingers from the left and the right. If they're approaching the same spot, then that limit exists for the two-handed limit. So let's look at a couple examples using this graph. Now, you don't have to write this. What if I ask you to find the limit as x approaches, let's say, 5 of f of x? So first thing I'm going to notice, there isn't any markings right up here above the 5. This is a two-handed limit. So what I need to do is I need to figure out, here's 5. This is when x equals 5. I'm going to approach the graph from the left. Where is this going as I get closer and closer to 5? What's its output reaching? -3, right? That's the output, so we're getting closer to -3. Now, that's from the left-hand side. Are we approaching it from the right-hand side as well? Are they approaching the same spots left and right? Yes? No? Okay. You guys are just staring here. That means the limit actually exists. Now, I could write it this way as well. The limit as x approaches 5 of f of x from the left. If I put that little negative there, it's not -5. This is saying you're only looking at the left-handed limit here. So that is just approaching wherever it stops at 5, which is also -3. Likewise, what if I approach from the right-hand side? Maybe I'll do that blue. So if I approach from the right-hand side, it's the same value. Which means if the left-hand side and the right-hand side are the same, then the two-side limit is equal. Now, that's a special point because this part of the graph is continuous. But what if I change it and I say, I want you to find the limit as x approaches 2 from the left. So why don't you guys figure these ones out in your head right now. I'm going to give you 3 of them, and I want you to kind of see what you can determine. We have to be careful because it's all based off of notation. This first one that I gave, this is saying approach 2 from the left-hand side. So you're only going from the left-hand side for this one. So, what did you get for the first one? Well, so that's part of the reason why we're doing this is there is that open circle there, right? But the limits don't care what's happening at the specific point. It's as it gets closer and closer and closer. So this is, if I look at this function, we have f of x approaches 2. So here's 2. Now I'm going to approach it from the left-hand side, which is coming in it this way. So my outputs are getting closer and closer. And eventually, where is this output going to head? -5, right? Now, will it ever get there? No, but it's going to get to -4.9, -4.99, -4.9999999. It's going to get so close that we're going to call that limit approaching 5. All right, now, what about the right-hand side? Now I have a little plus here. That tells me to look at the graph coming in from values of x that are greater than 2. So 2.5. Right? That's right here, right? If x is 2.4, that's about right there. How about 2.1? How about 2.001? What are we getting closer and closer to here? -7. Now, will we ever truly reach that? No. But we're going to get so close to it. Now, look at the notation here. Does the limit, and notice there's no markings here. This is my two-handed limit, which, or sometimes people call it two-sided. You don't even need a graph to answer this question. Does the left-handed limit equal the right-handed limit? No. If you were to point your fingers, they're pointing in different directions or different numbers. So because the left-handed and right-handed limit don't equal each other, our function, our two-handed limit, cannot exist. Now the one question that's always nice to throw in there after this is, what's my answer to this? What is f of 2? Remember this? There's no limit. There isn't any word limit, so this is just a location for the point. Now you're looking for the filled-in circle. So when x is exactly 2, when x is 2, it's filled in circle. It's right there at negative stuff. Yeah, so you do have to know the difference between just a regular point and the limits. Well, no, this means as I approach it from the right side and the left side, my fingers would not touch. Right? So it just doesn't exist because the left-handed limit and the right-handed limit aren't the same. If these were the same, then they would touch and they'd be hitting each other, so they'd be approaching the same value. A two-sided limit has to have both the right and left meeting together. The location, this is just a single point, right? That's a point as to when x is 2, where is 7. Notice, the point does not have to match any of these values. It happens to match the same as the right-handed limit, but it doesn't have to. Okay, I'd like you guys to try this one. And if you want to write this down, you can, but I'd like you to just answer it. I'd like you to find these 4 values based off of the graph provided. So I'm going to use highlighters here. Let's deal with the point itself. Notice, there is no word limit here. This is the location. Where is the location when x is negative 4? 0. Where's the dot? So that's equal to 0. Now, let's look at, that might be hard to see, there's a line there. So this is the left-handed limit. As I approach negative 4 on the function f, so I have to be on the graph. As I approach negative 4 coming in from the left side, where is my output headed? Negative 1. Yep. And then let's go to, what if I approach negative 4 from the right-hand side? So now I'm coming in from the right-hand side, and I'm getting closer and closer to negative 1. Now, without even looking at the graph, if my left-handed limit is equal to the right-handed limit, does the two-handed limit exist? So I don't even need the graph, and I know the answer is 1. Now, I love this example because it shows that the limits can all exist, and notice, it doesn't have to equal the point. Limits aren't what is the exact location. Limits are as you approach it and get closer and closer, where are you headed? Okay. All right, try this one really quick. You know what? Let me just do that one. Shoot. Let's scratch. We already did that one. No, I know. Didn't I just do that in this example? Right here? Yeah. So I was trying to be smart making it up, and then I forgot that we already did that one. So we'll skip that. But I do want you to notice one thing here quick with this example. Notice this graph. The left-hand side and the right-hand side aren't going to meet each other. Have you guys ever talked about jump discontinuity? I thought we did a long time ago. The beginning of the year, when we have jump discontinuity, when the graph is no longer connected, that's a sign that your left-handed limit is not going to equal your right-handed limit. So therefore, without even looking at the graph, I know that that two-handed limit is not going to be equal to each other. So I had done this problem a little too soon, but my thought was, how do we know, just by looking at a graph, if limits are or not, or they're not going to work? And there are 3 different types. You don't have to write this, because this is just getting your mind set. But there's 3 cases in which a limit would not exist. The first one is if the left-handed limit and the right-handed limit do not meet the same spot, right? Coming in from the left, coming in from the right. A quick way to tell, or to justify why that doesn't work, is that concept of jump discontinuity that we talked about. Okay, so jump discontinuity is kind of something interesting. The other one, and this is the important one that we're really going to get into next Thursday. What if I approach -1 here? So take a look at this graph. So here's -1. As I approach -1 from the left, where is my output headed? What are the y values? If I get closer and closer to -1, this graph keeps going up and up and up. Where is it eventually going to go? Is it 100? Is it 200? Infinity, right? It's going to an infinite level. So in this case, if I look at the limit as x approaches -1 from the left of f of x, that's going to infinity. Now, infinity is not a number. It's a concept, because we can't ever reach it. So we're going to a place that we can't ever get to. Now, does this limit exist? Not technically. Limits are an exact output. Okay? So if you see the answer is infinity, officially, infinity just tells us the direction, right? It's headed up towards positive outputs. But really, we're never going to get there, so that limit doesn't exist. And what if I did the limit as x approaches -1 from the right? Well, notice that's headed in the same direction. This is going towards infinity as well, but we're going to refer to it as it does not exist because infinity is just the direction it's in. But notice, technically, will my left-handed limit ever reach my right-handed limit? Not really. They're both headed in the right direction, but they're never going to touch. So that's why we would say the two-handed limit here does not exist, because they physically aren't ever going to reach the same spot. They're approaching it, but they'll never get there. This is why I didn't want you to write any of these. There's something called oscillating. I rarely see this. This happens on special functions that, what if you have a graph that just keeps going, and we don't really know what's happening. If I tell you to find the limit as x goes to 0, it doesn't exist because I don't know where I'm going to be from the left and the right. So if you see a function that's really crazy at special points, you're rarely going to see it, but that's called an oscillating function. It goes up and down, and there's not really any true behavior to it. So, this is the last slide, I believe, and I definitely want you to write this one down. Because, do we need a graph to answer these questions? The answer is no. There's a graph here, it's hidden. But we're going to be able to answer these questions without the graph because of what we know with the function itself. Now you'll notice what came into play here. It's a piecewise function. So you have to have some familiarity with piecewise functions to be able to become really good at this. Here's what my students in calculus struggle with the most. Because they didn't have the strongest piecewise background. We know that f of x has two different pieces. One is a parabola and one is a linear function. And then it says if x is less than 3. All right, well, what if I tell you to find the limit as x approaches 3 from the left, 3 from the right, and 3, and then the point? My question to you is which numbers are going to be to the right, or excuse me, to the left of 3? Is it the ones where x is greater than 3 or less than 3? You have to read the domain to help you out. Right? Numbers less than 3, 2.01, 2.002, 2.5. This is going to determine my left-handed limit. So how do we do that? Well, we're going to take the fact that I want to be close to x equals 3. Oh, you should write this. If you didn't write this, make sure you do it. And we're going to actually take the equation for the left-handed limit, and we're going to just plug in positive 3. And notice, it's not a negative 3. That negative, we're going to have a negative in front. The negative that's there refers to the left-handed limit. So we're just going to plug in 3 and then evaluate. What do we get? We get 9 minus 9 minus 2. The left-handed limit is negative 2. Nothing super crazy, it's just plugging it in. But then I have to figure out, what if I approach from the right-hand side? Well, the right-hand side has a different equation to it. Okay? Part of the different pieces. So my right-handed limit would use numbers that are greater than 3. So I'm going to take the new function for the right-handed side and say opposite of whatever x is plus 4. In this case, we're plugging in 3. So negative 3 plus 4 is a positive. What about, there is no marking, this just says as x approaches 3. That's my two-sided limit. What's the answer? Doesn't exist, right? Why? Okay. So, remember when I told you calculus was graphs, tables, equations, algebra, and verbal? When I ask you why, that's the verbal part. And that's where students really struggle. But it's exactly right here. Just like you said, the two sides don't equal each other. So the answer is does not exist. The reason is all you have to say, and look at the notation. This is where kids struggle, so I might as well show you it now. The left-handed limit does not equal the right-handed. That's written in math speak, right? My left-handed limit is -2, my right-handed limit is 1. If they're not equal, then the two-handed limit cannot make, it doesn't exist because the left-handed side doesn't touch the right-handed side. All right, now a non-pre-calculus question. F of 3. That's just the point. Right? That's the location when x is equal to 3. So which piece of our piecewise function tells me to use f of 3? Is it the top one or the bottom one? Bottom one. Why do we know we have to use the bottom? That little equal to sign says whenever x is equal to 3, we have to use that equation. Now, do I have to do any work to find it? No, didn't we already do that right here? If you want to, you can do that, just so it's there in your notes. All right, I'd like you guys to do these two right here. With the exact same formula. Let's see what you think about that one. Let's take a look at these. These are kind of tricky. I was curious how you're going to approach them. Notice, these are both two-handed limits because there's no plus or minus, so both sides have to meet. but it's saying x equals 2. Well, if x equals 2, is 2 less than 3 or greater than 3? Less than. So that means that I would have to use the left-hand equation. And since this entire left-hand side is continuous for its entire domain, it's a parabola the whole way, except for when it breaks up at 3, that means the left-hand and right-hand limit are automatically the same. So all I have to do is take the equation that's given and plug 2 in. It's direct substitution. What do we get? We get 4 minus 6 minus 2, which is negative 4. Now, the next one, what about x equals, as x approaches 5? Well, 5 is greater than 3, so we have to use the bottom equation. It would be the opposite of 5 plus 4, which is negative 1. Okay. Now, we did all of this without a graph. Go ahead and confirm this really quick. Confirm these two with your graph. Let's look at this. As x approaches 2, well, here's where 2 is. If I'm right here at 2, does the left-handed side meet the right-handed side at 2? And then where do they meet? 1, 2, 3, 4 down. So we confirm that one. What about as x approaches 5? Well, here's 3, 4, 5. So as I approach it from the left and the right, where are we headed? Towards negative 1. So if you have a graph, you don't even need the equation. Alright, last thing. Let's confirm these answers. What about at 3? The left-handed limit from 3. So I'm going to approach 3 from the left. That's coming right up here. Where is it headed? It's headed towards negative 2, the output. And then let's look at 3 from the right. If I go 3 from the right, that's jumping on the other branch of the piecewise function, and that's headed up here towards positive 1. Notice the jump discontinuity. You might have been able to conclude, because the left and the right-hand limits aren't equal, that there is a jump discontinuity without even knowing the graph. So therefore the limit can't exist, and then the final piece, f of 3 is equal to negative 1. If I go over f of 3, ooh, this graph isn't accurate. Positive. Yeah. It is so good, not screwing up. Of course, only natural. It is accurate. Alright, so there you go. That's the introduction to limits. It's all notation and reading graphs. And we're going to get a lot more into the equation side coming up. Okay? So, delta math is perfect for limits because it gives you good feedback as you go along. And the homework tonight is 12-1, day 1.